Hello and welcome back once again. So, our topic of discussion right now is fatigue behavior of aluminum based MMCs. And in the past couple of lectures, we discussed about stress controlled and strain controlled fatigue of metal matrix composites. In this lecture today, we are going to discuss about fatigue crack initiation and growth in MMCs. So let us first talk about the mechanism of crack initiation in metal matrix composites. So if you talk about particle reinforced MMCs, fatigue cracks can initiate into the matrix or at the particle matrix interface. It has been found that in both short fiber and particle matrix reinforced composites, the crack generally initiates in the matrix near the poles of the reinforcement. So let me show you a schematic of a particle reinforced composite, and then we'll see where exactly the crack initiates using that schematic. So here is a schematic of a particle reinforced metal matrix composite. So here you can see that the particles are distributed in the matrix. Now if you take a close look at the particles, you would see that there are corners or sharp edges. For example, if you see this particle, you can see sharp corners, right? So areas like that will be the sites for crack initiation, right? Because those would be the areas where there could be stress intensification. Okay, so the crack would tend to initiate near the poles or corners of the particles like these sites. Okay, as I said. And the other thing that you can note about the interaction of the particles with respect to the propagation of the crack, especially in smooth bar samples, is the fracture of the particles. And the number of such fractured particles has been found to be a function of the applied stress. Okay, and it has been also observed that the number of fractured particles increases as the crack progresses away from the initiation site. And this indicates a dependence on stress intensity. The stress intensity in case of fatigue testing, as we have discussed before, is given by this stress intensity range delta K. And in long crack samples, it has been found that particles are debonded at low delta K values. And the propensity of fractured particles increased with increasing particle size. And it is attributed to the presence of defects in the reinforcement particles, right? So larger particles are expected to have higher number of defects, and as a result of that, large particles are more prone to fracture. So decreasing the range of particle sizes will have a beneficial effect on the fatigue life of the composite by eliminating the fracture prone large particles. Okay, so this is how the crack initiation occurs in metal matrix composites. Now let us talk about the crack growth mechanism. Fatigue crack growth, if you recall, is characterized by this particular plot between the growth rate, that is dA by dN, plotted against the stress intensity range delta K. Okay, and delta K is nothing but K maximum minus K minimum, where K is the stress intensity factor. This can be also written in terms of the applied stress, because K is equal to sigma into square root of pi A. So for K max it will be sigma max square root of pi A, and similarly for K minimum it will be sigma minimum square root of pi A, where A is the crack length. Okay, this typically gives you a sigmoidal plot, as we have seen before while discussing about the general fatigue. Okay, so this plot, as you might know, has three regions. This is region 1, which is characterized by a threshold value of delta K, below which there is no observable crack growth. Okay. Region 2, as you know, is known as the Paris region. Which is basically the straight line portion when the crack growth rate is plotted versus delta K in a log scale. So this region is defined by this equation, as you might know. And therefore in the log-log plot, the slope of this straight line portion is m. Okay, and region 3 is the region of rapid crack growth, and here K max approaches Kc, the fracture toughness of the material. And the other important thing that can be noted over here is the fact that in the near threshold or near delta Kc regimes, the crack growth rate can be very sensitive to the microstructure and the load ratio R. Okay, so load ratio R can be given as K minimum by K maximum, which is also equal to sigma minimum by sigma maximum. So on this plot, for example, if I show another curve for high values of R, then it will shift towards left. Something like this. So this is for high R, and then this will be for low R. Okay. However, the microstructure and the load ratio have smaller influence on the crack growth rate in the Paris regime. So when you talk about the fatigue crack growth behavior, it will be defined by the Paris constant, the crack growth threshold, and the fracture toughness. So now that we had a quick review of the general fatigue crack growth behavior, let us go ahead and see the fatigue crack growth in metal matrix composites. So the data presented here on fatigue crack growth in MMCs are generally collected from fatigue tests conducted under constant R at values less than 0.3. And under such conditions of low R, it has been assumed that the introduction of the reinforcement phase results in a higher threshold, a steeper Paris region, and a transition to unstable fracture at lower delta K values. So these are the three assumptions, that due to the presence of the reinforcement phase, there is a higher threshold, steeper Paris region, and a transition to unstable fracture at lower delta K levels. This one has been attributed to lower fracture toughness of composites. But the behavior in the near threshold and mid-range regime is not that straightforward as far as metal matrix composites are concerned. Although it is difficult to categorize these observations, but a majority of them will fall under one of these three categories when you talk about the fatigue crack growth behavior in MMCs. Number one, an increase in the threshold, and an increased dependence of growth rate on delta K in the mid-range regime. This also means a larger value of M. Okay. Second, lower delta KTH, and higher near threshold and mid-range growth rates. And number three, lower or equivalent mid-range growth rates, and lower delta KTH. So we are going to take examples of each of these three situations. For example, the first kind of behavior was exhibited by this composite 2080 aluminium 15 volume percent silicon carbide particles in T6 condition. Okay, and it was at a stress ratio value of 0.3. Okay, so this resulted in a modest increase in the threshold and a steeper slope in the mid-range growth regime. Okay, so if you look at the growth curve for this particular composite and compare it with the unreinforced material, it will look like this. This one is for the unreinforced alloy. And this one is for the composite. So here you can see the first type of behavior, that is there is an increase in the delta KTH, right? That's what you can see for the composite. But the mid-range growth rate in terms of the slope M is higher in the composite. Okay. Now let us take the second type of behavior, that is lower delta KTH and higher near threshold and mid-range growth rate. This kind of behavior was displayed by a composite of aluminium 3.5% copper reinforced with different volume fraction of silicon carbide particles, and this was at R equals to 0.1. Okay, so here the delta KTH value for the composite was lower. So if you look at the plots, so the unreinforced alloy was somewhere around here, and the data for the composite were found at the left. Okay, so that's what this means. Okay, lower delta KTH as the particles are introduced in this matrix. Okay, so the composite were somewhere around this region. Okay, so composites with different volume fraction of silicon carbide lie to the left of the unreinforced alloy curve. And you can also see that in the mid-range regime, it is steeper. So that means the growth rate is higher. Okay. Even in the near threshold region also, the growth rate for the composites was found to be higher. Now let us take the third kind of growth behavior, that is lower mid-range growth rate and lower delta KTH, and that kind of behavior was exhibited by this composite, a composite of this 7000 series alloy with a typical composition of this. Reinforced with 15% silicon carbide particles, and this was also at a stress ratio value of 0.1. Okay, so here the behavior looks like this. If you look at the growth rate of the composite in comparison to the unreinforced alloy, this is what was observed. Something like this. This blue one is for the composite, and the black one is for the unreinforced alloy. Okay, so here you could clearly see that the delta KTH is lower for the composite, and the mid-range growth rate is also lower. Mid-range over here, if you look at this region, that is the Paris region, the growth rate is lower. So that's the third type of behavior that we categorized before. Okay, so all three kinds of behavior can be displayed by metal matrix composites, depending on various factors such as the load ratio, the kind of sample or the kind of test technique used, and so on. But as I said before, most of the data will fall under one of these three categories. And with that, we come to the end of this lecture. Thank you for your attention.